Let's pull the costs together and then look at the bugs that catch people. First, the price of each operation, then the common mistakes in C. Read this table like a receipt. Every cost has a visible cause. Cheap work ignores the other cells. Costly work touches a whole run of them. Let's go down the list. Access A at index I is big O of 1. The address is base plus I times the element size. That is one calculation and one read. Update A at index I is also big O of 1. Same address, one write. The size does not change. Traverse is big O of n. We make one visit for every element. Insert at the end is big O of 1. We write at the index equal to size, and nothing else moves. Insert in the middle is big O of n. We write shift up to n elements to open a hole. Delete in the middle is big O of n2. We left shift up to n elements to close the gap. Linear search is big O of n. In the worst case, we scan every element. Binary search on a sorted array is big O of log, and each comparison halves the interval. Now a quick check. You keep a sorted array. Each round you do two things. First, you look up a value. Then you insert a new value in its sorted spot. Which step sets the pace, and what is the total cost per round? Pause and think before the answer appears. This is the answer. The lookup is big O of log n by binary search. But the insert still shifts elements, so it is big O of n. The shift is the slow part, so each round is big O of n. A fast search does not fix a slow middle insert. That tension is what pushes us toward later structures. Let's look at 5 common array bugs in C. For each one we name the mistake, the symptom you see, and the fix. First bug, reading or writing A at index size or at index -1. Both are outside the array. You get a garbage value or corruption or a crash. The fix is to make sure 0 is less than or equal to I, and I is less than size before every access. Second bug, mixing up size and capacity. Size is how many values you have. Capacity is how many slots you reserved. If your loop runs into the spare slots, it reads uninitialized data. So loops must stop at size, never at capacity. Third bug, an off by 1 in the loop bound. Writing less than or equal to where you needed less than. That touches index n, which is 1 past the end. The fix is to use I less than n. The last valid index is n-1. Fourth bug, running the insert loop from front to back. That smears one value across the whole tail because you overwrite cells before you move them. The fix is to copy back to front, away from the hole. Fifth bug, forgetting that insert needs room. If the array is already full, you write past capacity, and that is a buffer overflow. Always check that size is less than capacity first. Let us look at the most common array bug in C. It is called the off by 1 bug. The loop stops one step too late and reads one slot past the end of the array. This is the buggy version. The loop guard says I is less than or equal to n, so when I reaches n, the loop runs one more time. It reads A at index n, but an array with n elements has valid indices 0 up to n-1. So A at index n is 1 past the last real slot. What happens? The sum picks up a garbage value from memory the array never owned. The answer changes from run to run. In C, this is called undefined behavior. The program does not stop with an error. It just gives you a wrong result. This is the fix. Change the guard to I less than n. Now the loop visits only indices 0 up to n-1. It never touches A at index n. The rule to remember is simple. An array with n elements has last index n minus 1. So the loop guard is I less than n, never I less than or equal to n. One more warning. You may think that writing at index n just adds one more element, but it does not. Index n is one past the last live cell. Reading it gives you garbage. Writing it stamps your value onto memory the array does not own. The array does not grow to meet your index.